All right, continuing on with acid and base chemistry, let's go ahead and answer a couple of brief questions. Which base of the following is the weakest? So we can see on the figure that base strength decreases as we go from the bottom to the top in the column of our conjugate or Bronsted-Lowry weak bases. So if we go through them one by one, we can see that fluoride is weaker than ammonia. Hydroxide is a given. We know that that is how strong base exists in an aqueous solution. It's all the way down there. Sulfate at the top. Sulfate is a relatively weak, not quite a negligible, but a relatively weak base. And then we have acetate at the bottom. So we can actually put these in order, right? So hydroxide being the strongest, then moving on to ammonia, then moving on to acetate, moving on to fluoride, and sulfate being the weakest. Now let's look at the other column of our weak acids. Which of these acids is the strongest? So let's take the same approach, and we notice that acid strength increases as we go up this column, right? So we've got our strong acids at the top, right? Hydronium, that's an indicator right there, right? It's the form that these strong acids have in water. So we can go through, we see water down here at the bottom, right? Water is not a particularly strong acid, though it does act like a Bronsted-Lowry acid and a base, depending on what you have with it. HF, or hydrofluoric acid, is right there. It's a stronger weak acid, right? Right underneath it is acetic acid, and then we have the ammonium cation, right? The conjugate acid of ammonia, the weak base. And we can look at that and we can see, again, we can rank them, right? Strongest to weakest. We would put hydronium, in this case, being our strongest acid, HF next. Then we go down to acetic acid, ammonium, and water. Our answer there would be that hydronium is the strongest acid in this case. Another topic of these Bronsted-Lowry acid-base equilibrium processes that's not really discussed in our text is when we have one of these equilibrium systems, which direction is equilibrium going to favor? Are we going to push more towards the product or back towards the reactant? So in these processes, which direction is equilibrium going to be favored? The key to identifying the direction of equilibrium is the strength of the base on either side of the reactant. So comparing water as a weak base to chlorite as a weak base, we can go over to our tables here. We can find water right there, but chlorite is not on our list, and that might cause us some confusion. But what we do know is that that is the conjugate base of chlorous acid, or a weak acid. Therefore, its conjugate is going to be a weak base, slightly stronger base than that of water. We could say that it falls down in here somewhere. So that would indicate that the stronger base will push equilibrium the opposite direction. Go ahead and identify your bases on the next three reactions. Compare their strength in terms of being a base and predict which direction equilibrium will be pushed. In the second reaction, we've identified ammonia on the left-hand side and hydroxide on the right-hand side. Comparing their relative base strengths in our chart, we can see that hydroxide is the stronger base. That will push equilibrium back to the left. In the third reaction, we've identified ammonia on the left-hand side, hydrogen phosphate on the right-hand side. We compare their relative base strengths, and we see that ammonia is slightly stronger base than hydrogen phosphate, so that is going to push the reaction to the right. And in the last reaction, we've identified carbonate on the left-hand side, sulfate on the right-hand side, comparing their relative base strengths. Sulfate is a very weak base, carbonate is a stronger weak base, and so we can say that the carbonate is going to push the reaction to the right. So recall our strong acids. These are the acids that we say completely dissociated, and we were asked to memorize 7 of them. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. So I'm going to represent any generic acid with this HA, right? So here's our acidic proton, the H, and then the conjugate base is just that A part of the molecule. So what happens in water is that the strong acid completely dissociates, right? We have an arrow going left to right, a single arrow, forming the conjugate base of the strong acid and hydronium. So one thing to consider is that when this happens is, let's say we were to start off with maybe 0.1 molar strong acid in solution, that completely dissociates. And what that forms for us is 0.1 molar of the conjugate base and 0.1 molar of hydronium in solution. So for a monoprotic strong acid, we can say that the concentration of the strong acid that we start with, as we saw right here, is equal to the concentration of hydronium ion in solution. So let's just go through monoprotic, diprotic, and triprotic acids. A monoprotic acid seen here, what that's saying is it has one acidic proton that it can donate or that it can lose, and that's what we see in this reaction equation that we have up here with our generic monoprotic acid. When we get to a diprotic acid, it's saying that there are 2 acidic protons. A good example of this is sulfuric acid. Sulfuric acid has 2 acidic protons. The first proton comes off as strong dissociation, meaning that first proton completely dissociates. And then that leaves us with bisulfate here, which is a weak acid. So it is in equilibrium for that second acidic proton. And an example of a triprotic acid, although it's weak, is phosphoric acid, which has a first dissociation in equilibrium to remove the first proton, form a weak acid which has a second dissociation, and then a third dissociation. Right? So we have monoprotic, diprotic, and triprotic acids. Our strong bases are the hydroxide salts that dissolve completely, that dissociate completely. And these are the group 1 alkali metals and the calcium, strontium, and barium salts of hydroxide from group 2, or the alkaline earth metals. So when we have aqueous solutions of these salts, of these hydroxide salts, they completely dissociate, showing with the single arrow, into their representative ionic species: sodium hydroxide, sodium cations, hydroxide anions, potassium hydroxide, potassium cations, hydroxide anions, strontium hydroxide, strontium cation, and hydroxide anions. Notice the stoichiometry here with the 2+ salts here for calcium, strontium, and barium are going to yield 2 equivalents of hydroxide in solution. So let's look at what this means for concentration in solution. If I have a 1 molar solution of sodium hydroxide, what we really have in solution is 1 molar hydroxide. If I had a 0.5 molar solution of potassium hydroxide in solution, we have 0.5 molar hydroxide. If we have a 0.1 molar solution of strontium hydroxide, notice that the stoichiometry is 2 equivalents of hydroxide to every 1 equivalent of strontium hydroxide. A 0.1 molar strontium hydroxide solution is going to give us 0.2 molar hydroxide in solution. So the way we measure the relative acid strength between all of these weak acids is through their equilibrium process, right? So we can see this generalized acid dissociation equilibrium process where the weak acid dissociates to form the conjugate base and hydronium. And just like any other equilibrium process, we can set up an equilibrium expression where we take the equilibrium constant, equilibrium expression constant, is equal to concentration of products over reactants. Recalling in this case, right, water is a pure substance, a pure liquid, so it appears as a 1, or in this case, we leave it out. The equilibrium expression for a weak acid that we see right here has a special designation. We call that a weak acid dissociation constant. And so instead of Kc or Keq, we designate that as Ka, and that is defining weak acid dissociation constant. So here we see a table of a variety of weak acids, right? So we've got a variety of weak acids here. We can show their structural formula with the acidic proton here. When we take that proton off, we see the conjugate base formula there. Their equilibrium reaction equations we see written out here. And then we have their acid dissociation constant, the equilibrium constant for a weak acid, and those values are here. And we can think of any weak acid dissociation for a monoprotic weak acid as HA, or this weak acid, dissociating in water to give the conjugate base and hydronium. And we can set up that weak acid equilibrium expression as the weak acid dissociation constant Ka is equal to the concentration of the conjugate base times the concentration of hydronium over the equilibrium concentration of that weak acid. The numerical value for that weak acid dissociation constant, Ka, is directly dependent on how much of that acid dissociates. The more acid that dissociates, the more hydronium that we're going to have in solution. The more hydronium we have in solution, the larger this numerator value is going to be, slightly smaller denominator value. It's going to increase the value for the Ka. So what that means is the larger or the closer to 1 that value gets, the stronger the acid because the more it dissociates. So if we take a look at our table, if we go from hydrofluoric to nitrous to benzoic to acetic to hypochlorous to hydrocyanic to phenol acid, right, we can see that these Ka values are getting smaller. So in this case, acid strength is going down as that Ka value gets smaller. If we consider the dissociation of a strong acid to its conjugate base and hydronium, we could set up an equilibrium constant expression for that where Ka is equal to conjugate base times hydronium over the equilibrium concentration of your strong acid, which through complete dissociation, that's essentially 0. And what that means is that equilibrium constant for that strong acid is much, much, much bigger than 1. So let's consider a few questions. In these scenarios, which acid is weakest? So our weakest acid is going to be the acid that has the smallest Ka value. So we can see that here, hypochlorous acid is the weakest. It has the smallest Ka value. Which acid is strongest? So this is a little bit of a trick question here because you have to recognize that HCl is a strong acid compared to these other weak acids. It is going to have the largest Ka value. It is going to be the strongest. And our third here is which weak acid is going to be the strongest. So we'll only consider these 4 in that question. Which weak acid is strongest? So which acid has the largest Ka value? And that is going to be hydrofluoric acid that we see there. Now to challenge you just a little bit further, let's answer these questions as they're phrased. Which acid has the strongest conjugate base? And which acid has the weakest conjugate base? Go ahead and hit pause, and we'll be right back with the answers. So when we're looking for conjugate base strength with respect to the acid, we need to recall the relationship that the stronger the acid is, the weaker its conjugate base is going to be. And the weaker an acid is, the stronger its conjugate base is going to be. So this question is asking us, which acid has the strongest conjugate base? which means we need to look for the weaker acid. The weakest acid here is going to have the smallest Ka value. The next question is asking us to find the weakest conjugate base. So the weakest conjugate base is going to be the strongest acid. So in this case, we know that hydrochloric acid is a very strong base. It's got a very large Ka. Therefore, chloride, its conjugate base, is going to be negligible. The answer there is E.